Kulki tells Joe Pesci and the other guy, you guys are, you've had enough or you're thirsty for more. So this is actually part 2 of the talk this morning. Trisection Algorithms. And I dedicate the talk to Joe Horn, who I consider the pinball wizard of number rounding. A week or 10 days ago, I was trying to write a HP prime program that converts from decimal to fraction, and I put it on the website. And then I said, well, I'm going to write another program that is a little bit more efficient, and that's where I got in trouble. Well, I guess I'm a bigger man to admit my mistake. Bigger in a sense, my behind is still swollen from the ass kicking I got. I told my son, I said, this is one minefield I should have not gone into, but thank goodness for humor and forgiveness. So, thanks, Joe. My better creed is the much better is also the enemy of the good. So, of course, again, there's always opposition, and Freud here says it's just in my dreams. The trisection method, as the name suggests, is very similar to the bisection method. You have a root bracketing interval, and instead of cutting it in half, it cuts it in thirds. But I figured, well, we choose a first point. There's going to be potentially x1 and x2. And we choose the point x1 in the interval AB closest to either the end point A and B that has the smallest absolute function value. That was the strategic choice I made in designing the algorithm. So I'm going to call that endpoint Z. And I look at the product of f of x1 and f of z. If it's negative, then we have the brand new shrunken interval, and the iteration has finished its test. It's done. We go to the next one. But if these two function values have the same value, then we calculate x2, and only then. And we see which at x2 is closer to the other interval endpoint. I'm going to call that y. And it becomes a simple matter of asking from the function, the signs of the function values, whether x1, x2 is the new interval, or x2, y, meaning the other endpoint is. And that's what each iteration does until, of course, the interval a and b shrinks to within the tolerance, hugs the root we're seeking. And here's a simple HP prime program with my favorite function e to the x, and I have trisect. Again, the parameters are the interval defining a, b, the tolerance value, and then I have a call here. The trisect, I give it the interval 3 and 5, and a small tolerance value, and it gives me root around 3.733. The trisection plus method simply takes that approach and adds a linear, or actually, if you want to be exact, inverse linear interpolation. And I'm going to explain the method actually using graphs because it's better. A picture is worth 8,000 words. Here's an example, for example. Okay, I start with x1. I calculate it. And I say, oh, fx1 and fa have opposite signs. So I'm going to draw the line between x1 on the curve and a on the curve. Get x3. And then look at its function value. In this specific diagram, fx3 and x1 have the same sign. So conclusion, the new shrunken interval is ax3. Had fx3 been on the other side of the curve and the same sign as fa, then the new interval would be x3, x1. I do all that without worrying about the other point. Not necessary in this case. But if fx1 and fa have the same sign, and remember, these could be symmetrically, like the values could flip. Then I go and calculate x3, which is closer to the other end, x2, which is closer to the other endpoint b. and then draw the line between x2 on the curve and x1 on the curve. Get x3. And then look at its value, compare it with either one. Let's say in this case, since these two values are on the same side, below the x-axis, then the new interval is simply x3, x2. Had the reverse been true, then the interval would be, if it's above, would be, oh, sorry. I'm trying to picture it in my mind.
X1 to X3.
Yeah. Thank you. That's right. Yeah. Then fx1 and fx3 and fx1 have the opposite sign. Then it's x1, x3. Thank you. The case 3 is where. Oops, sorry. Case 3 is where fa, fx1, and fx2 all have the same sign. In this case, it's this image. They're negative. They could be, symmetric. They could all be positive. Then we say, okay, we're going to draw a line between x2 on the curve and b on the curve and get x3 there. And then look at its sign. In this case, fx2 and fx3 have the same sign, so the new interval is x3, b. If not, it would be x2, x3. And then here's an implementation of the trisection. Sorry. Here's an implementation on the HP prime. Again, I have the. Now you notice there's a function. Oops, sorry. There's a function called interpolate. So I need to do the linear interpolation, and then it's called by trisection plus. I have the, you will find in the jump drive of the conference text files for the listings on the HP Prime for all the routines of this morning. In the case of the trisection, in some of the cases I've included a second version in the file name you see version 2, where I store the intermediate values in matrix M0. And that will give you an idea of, thank you. And that will give you an idea of the progress, the intermediate values that you can see. Here's a screenshot, for example. So if you want to trace, because the routines I wrote, I just give you the answer. I don't even bother with the number of iterations. But here, it kind of sort of, it's an audit trail of how it got to where it got. So here again is a table of comparison. We have the various function cases we're testing, the initial root bracketing interval. We have the tolerance and the function tolerance values, the roots that I'm aiming at, and then the various algorithms. We have trisection, bisection, trisection plus, and then Newton. The trisection is clearly faster than the bisection. So the gamble of, picking the right end and aiming at hoping that the initial interval would be sufficient per trial seems to pay off. The trisection is by no means better than Newton, but the trisection plus is, I think, fairly in good competition with Newton's method also. And that's it. Thank you. And we're ahead of time a little bit. Questions?
Have you looked into expanding that to multivariable functions like f of x and y, and then kind of try to reach the root to x and then y and then x again?
Actually, you read about over 10 years ago, I was in Canada sitting in my brother's office. He has an internet service. And I said, you know what? There's no bisection method for two variables. And I tinkered and tinkered, and my website has I finally came on. But here's the problem. Selecting the initial guesses for two variables in a bisection method is difficult. But I was able to come out with an algorithm. It's on the web, and I think I wrote it in C++, something like that. But I tried to extend and I said, that's too difficult using bisection methods.
Because what I was thinking is in chemical systems,
yes.
Maybe you can box, like if you want the concentrations of various species, you can box them between 0 and your maximum value that you put at the beginning.
Okay.
So you can box it well.
Okay.
And Newton, for these systems where you have like very, large differences of orders of magnitudes that can be very large.
Yeah.
Newton sometimes it just throws you off. It's not super great. So
a few months ago, I was able to find an older paper that showed using Haley's method for multiple variables, and I implemented it, and it's very efficient.
Oh, okay. Yeah.
So I don't know if I published that on my website or not, but I know I was working on it, and I don't know if I finished it or not, but it seems to be also, the Haley's method is typically more stable than Newton's because it's using secondary. There's a price to pay, but also I think at the advantage of stability. A little bit more computational effort, but it's more stable, yeah. But yeah, the bisection for two variables, I figured it out, but it's like, how do you use it? Yeah, it's. But if you have a systematic system between 0 and something, yeah, that would be then an easy guess.
Yeah, because Newton sometimes throws you into negative concentrations which don't exist.
Yes, yeah.
What do I do?
Yeah, it gives you a solution that's mathematically okay, but realistically doesn't.
Right.
Yes, Jonathan.
So, how many different test functions did you apply this to, and do you have a sense of how true your conclusions are for a wide range of functions?
I mean, like I said this morning, I tried exponential, I tried some polynomial, although this one is a bit less. But, you know, the thing is, because these are all root bracketing methods, pretty much they're guaranteed to work if the initial, if you have one root in the initial interval, you're going to get there. So, and again, like the bisection, the inverse interpolation gives it a little bit more oomph, power. And if you're lucky, the first x1, if it's close enough, then you don't do. Now the code is long when you look at it in the HP Prime, or I even have it on the web as Excel. But it doesn't execute all the code because it's looking at where, studying different conditions, and it always executes only a few statements from a long set of statements in each iteration. It doesn't do the whole thing. So it may look extensive, but it's only because it's trying to find a decision-making path on what case are you in, and but it's fairly fast. All right. Okay. Thank you.